welcome to the show, Sean. How's it going?
Pretty good. How are you doing?
Not too bad. Not too bad. All right, Sean, do you mind please introducing yourself to the audience? Tell them what you do for AWS.
Excellent question. I work in AWS cryptography. I'm a senior software developer working on the AWS Libcrypto library and the AWS Libcrypto for Rust.
All right, so Adrian, this is the segment where we get our minds bended here, right?
Looking forward to it. Look, I'm genuinely willing and ready and able to allow my mind to be bent just a little more than it already is. Take away something that selfishly I've been wanting to get deeper into, and I really relish the opportunity to be able to hear that from an expert that we have in house. So, Sean, please take it away.
Yeah, so I'll start by telling a little bit about what is AWS Libcrypto. So AWS Libcrypto is a project we launched kind of late 2020. It's a fork of Boring SSL originally, which itself was a fork from OpenSSL kind of, a few years prior. There was Heartbleed and a few internet shaking events in the TLS space.
Oh, yes.
So we forked Boring SSL, made AWS Libcrypto, but why, right? There's a couple things. It allows us to deliver, optimize and perform crypto for both x86, 64-bit EC2 instance platforms, as well as many people may or may not know on chat, AWS has its own processors like AWS Graviton processors, and we've been able to have optimized cryptographic algorithms for those platforms that take advantage of the CPU features that are available, and kind of additionally deliver value for our customers who then in turn use AWS Libcrypto, whether that's through the AWS SDKs, or if that's even when you're talking to an AWS service, on the back end with an AWS, your connection's going through TLS and using AWS Libcrypto.
All right, Sean, I wanted to back us up a little bit before we get into, because we're gonna have to talk about what TLS is, all kinds of things like that. But I think we should start right at the beginning, right at the basics. When people hear cryptography, they most likely associate it to, hopefully, they most likely associate it to encryption, right? But cryptography isn't entirely encryption, right? There's also things like hashing and other things which serve purposes within the larger space of cryptography. But when we're talking about TLS, when we're talking about what we're going to be talking about today with Libcrypto, we're generally speaking about encryption. Is that fair?
Encryption, and when you're thinking about TLS, you've got a couple factors, right? You've got symmetric encryption, you've got public key cryptography, asymmetric encryption. In that case, you have hashing algorithms, you've got MACs, you got key derivation functions. There's a lot of moving parts that go into, hey, I'm typing in AmazonAWS.com into my web browser, and I'm getting the nice secure lock icon in the corner, and somehow my connection's secure. And like, what is the underlying pieces that make up that entire connection process? What makes it secure?
Yeah. Let's talk about that, right? So specifically with TLS, right? Used to a long time ago be called SSL, right? Which accounts for that boring SSL that you mentioned earlier, open SSL. That's why you might, when talking about TLS, see SSL still mentioned, but TLS is it's kind of like an amalgamate, a couple of things coming together to form, I guess I'll call it a protocol. I don't know if it's called that in the industry, but it's using a couple pieces of cryptography to generate something larger than just, hey, I encrypted this piece of data and sent it over a wire, right?
Correct. Yeah. So I mean, we can talk about the TLS connection process as a high level overview and talk about kind of the moving parts, right? So let's just walk through, right?
Let's first talk about what is TLS, used for, first off, and why is it important? Like, why are we?
I was about to ask, explain it to me like I'm 5 and I don't know anything about the internet, but when I pointy clicky button and it goes and does something, can we start there? Or is there a better way to approach that when someone internal says, hey, why is this important? I would love to hear your talk track there.
So let's say you're a 5-year-old who's managing your financial bank account, right?
Hey, there's a lot of people out there right now.
Yeah. So let's say you want to go purchase something on Amazon, right? Mm-hmm. You go to Amazon.com, and a lot of people these days are kind of attuned to, there's this nice, different per browser, but you've got a nice little icon in the corner. It might be green. It's got might say secure. It's got a lock, right? If you go to a website, sometimes you might see like a red X through it. You might not even see the lock. And we've kind of all come to see that as like, my connection's secure, my connection's not secure. Well, what makes it secure versus not secure, right? So for a non-secure connection, right? If I was making purchases, I was typing in things I want to search on the internet. That communication would be, plain text, right? Between my web browser, my client, to whatever the endpoint server is, right? Some bad actor, if they were able to sniff, the packets between those two connections, they would be able to see everything I'm sending, right? So if I'm typing in my credit card number to make my purchases, they would be able to see that, right? And we don't want people to be able to see, be able to steal our credit card financial information. We don't want people to snoop into people's lives, see what are you purchasing, what are you searching for, what's going on, right? That could be health information, etc. So TLS does one aspect, right, of encrypting the data connection between 2 points and ensuring that you can't have bad actors come in and decrypt to be able to look at the data that you're sending. As well as, they can't just randomly also send their own packets along and inject, nefarious information along the way. And that's just one aspect. Another aspect is, how do I know when I type in Amazon.com that's actually Amazon.com, right? Public key cryptography, right? The PKI, public key infrastructure. Yep. A certificate. Part of TLS is, either the client, the client can optionally say, here's my certificate of my identity. But the most common one you're familiar with from like the web browsing perspective is, a server saying, I am Amazon.com. Here is my certificate. This certificate is signed by some trusted chain that ultimately your, Windows, Mac OS, Linux, you've got trust storage of what are called like root certificate authorities that we all trust on the internet to say, like, if they sign a certificate and issue it for Amazon.com, they validated that whoever's requested that certificate is indeed Amazon.com. And that's how that's how we build this trust relationship of like, you're a user, you type Amazon.com, you get a certificate back, that certificate came from a trusted authority. It's not just somebody who made their own certificate, got it trusted on your machine. Now you're not really talking to Amazon.com necessarily.
And these public and private keys are then utilized to negotiate a TLS handshake, establish a symmetric key, right, that can be shared over the session and encrypt the
stuff. So there's a few moving parts. So part of the TLS connection is, hey, here's my certificate, and that certificate as part of the handshake process. When the server says, here's my certificate, it also says, well, how do I prove that I hold the private key that's associated with the certificate, right? So it'll take a hashing algorithm being a one-way function, right? You pass data into the hashing function, it spits out some fixed length data back, right? And it's one way in that you can't, try to figure out what inputs on You
can't
like,
reverse it
reverse,
back to the
right?
string. Yeah.
Yep. And then it's highly collision resistant, right? Is the goal. You can't have two different inputs to the hashing function result in the
same value.
output,
Yeah.
right. So as part of the handshake, there's a long string of handshake messages, right? Of like, what has the client said so far? What has the server said so far? The certificate will generate a digital signature using this hashing algorithm, and it will say, okay, here's the signature I've computed and signed of all the messages we've talked about so far with my private key, and it will give it to the client, and the client turns around and can say, okay, I will validate that signature you gave and verify you signed it using the public key from the certificate. And that's what, binds the, I just don't give a certificate and say, here's my certificate, I'm Amazon.com. I have to also prove to you I hold that private key. So that's one aspect of how certificates and public and private keys get used. Additionally, there's like a key exchange algorithm. You might have heard of like
Diffie-Hellman.
DHE, Diffie-Hellman. There's also ECDHE, which is elliptic curve Diffie-Hellman, where a client will come along and say, well, I've got here's a number I've generated, right? And the server says, okay, here's a number I've generated. And through some really cool mathematics, whether that's integer factorization problems or discrete logarithm problems, it depends on whether you're using RSA or Diffie-Hellman or elliptic curve Diffie-Hellman, we'll arrive to some common shared secret, right? And then that is used to then further derive keys for this TLS connection that are then used to feed the symmetric cryptography. Because ultimately, during the handshake process, you're working your way towards getting a symmetric key that you then use for the client and the server ends of the connections.
Got to get that shared secret, but you can't send it over an insecure channel, right?
Correct. Yes. So these are ECDHE and Diffie-Hellman. They're all key exchange algorithms to come up with, a shared secret over an insecure channel.
Well, Sean, we're here to talk a lot about the Libcrypto library. We're going to be talking about the FIPS features that you all have just added. Do you think now is a good time? I know you've got a demo for us. Should we just take a look at Libcrypto and see it in action, see some of the things that you've been working on?
Yeah, we can go through a demo. I guess I'll give a shout out real quick,
please,
of what we've done before we jump in.
Yes.
So part of our motivation for Libcrypto for Rust is FIPS, right? A lot of our customers, even AWS, has a story that they need FIPS crypto for government regions, right, to be able to provide to governments. So AWS Libcrypto got a FIPS certificate back in October last year, late 2023. And in April 2023, we had built a Rust library on our next iteration of our FIPS certification, right? So we have a FIPS certificate for AWS LC FIPS 1.0. We've validated for our next round of certification. We have a lab that's validated our 2.0 library, and that's pending a certificate being issued by NIST. NIST is the government body that manages the entire program. And Libcrypto for Rust is built on that 2.0 version, right? That's pending issuance of a certificate. And what that's enabled us to do is, we've worked with Rustls. Rust TLS is the open source project. It's a Rust implementation of the TLS library. And they recently made us the default provider for their library. So they're using AWS Libcrypto for Rust. And we've enabled cool things for them. So as an example, post-quantum crypto algorithms, there's a big space that's coming up.
Yes.
And one of the things we've been able to provide from AWS Libcrypto for Rust is support for Kyber, which is a post-quantum key exchange algorithm. Specifically, it's a KEM, key encapsulation mechanism. There's a lot of acronyms. I apologize.
That's the whole security realm.
Yeah. So what I wanted to demo as the clue in is Rustls, as of like, I think it was 2 days ago, they just launched their post-quantum support for X25519 Kyber 768 draft.
Yes.
It's a RFC proposal for how to do X25519, which is a ECDHE, it's a elliptic curve key exchange algorithm in combination with a post-quantum one, right? So you combine the two together. If there's a weakness found in the post-quantum algorithm, there's still not a quantum computer yet that can crack your classical cryptography, then you're still protected by the X25519, and then vice versa. If X25519 is suddenly broken, your TLS connection is, still using Kyber for a portion of it. So I want to demo that using Rustls and Libcrypto.
We're running short of time, Sean. So let's get to the demo. We do have a question from chat. We may need some extrapolation here. Greek Myth Guy asked, do you guys do anything with AI cryptography integration?
The AWS cryptography organization does have some services and libraries for the machine learning services, but off the top of my head, I don't remember what their names are. I apologize.
No worries. All right, let's get to your demo, my friend.
Let's hear it.
Drag some over. All right. So the first demo, since I know we're short on time, basically, I wanted to show off this X25519 Kyber 768 draft PR. So this is some Rust code. It's lengthy, I know. But essentially what we're going to do is I instantiate AWS LCRS as a Rustls cryptographic provider. I'm going to say, hey, I only want to talk to the ACM service, Amazon Certificate Manager service. I only want to use this new draft Kyber key exchange algorithm. And then I'm essentially going to construct a TLS client. I'm going to create a connection to the list certificates for calling the list certificates API. I'm going to set up my credentials. I'm going to do some SigV4, which also involves crypto.
Yeah.
And then we're going to call the service and we're going to get a response, right? So if we go back to here, if I do ACM, it's going to call ACM, and ACM came back and they said, oh, okay, you have no certificates in this account. I don't have any ACM certificates set up, but we got a request. And so you might be interested in saying, like, how do I know you actually use that key exchange algorithm? So I have another demo, which I think is kind of exciting. So the first demo, we used Rustls from a client perspective, but you can also go start a Rustls server using this new hybrid post-quantum algorithm. So if I start up a server real quick, let me get my cheat sheet. Make this easy. So I'm the start up a server, and then for giggles, kind of want to show a packet capture at the same time.
Ooh.
So I'm going to come over here. I'm going to make sure so Firefox has support for this Kyber post-quantum algorithm, but it's off by default. So I started up my local server, and I'm going to try to connect to it on 127.0.0.1. And I should get, oh, no, can't type. Live demo. Always goes wrong, right?
It lets us know that you're doing it live. Everyone knows it's part and parcel of live demo gods never participate.
Yep. So Firefox got an error. It said no cipher overlap. That's because my server, I have it coded explicitly only to support the Kyber key exchange algorithm. So if I had gone back to Wireshark here, basically my client came along and said, hey, I want to do X25I19 or SecP256R1, which is a elliptic curve. And the server said, nope, I can't do that. So if I come on and turn on Kyber now and reload the website, you'll see I get the message back that I connected with this key exchange algorithm. And if I were to come along back here in the client hello, you can see now that I configured Firefox, the client came along and said, hey, I could do X25019 Kyber 768 draft 0. And the server came back, and as part of its server hello, it will say, hey, we're going to do that. That's how we're going to do our key exchange. In this case, it's called key share in the TLS connection.
That's super cool, Sean. Now we are right at time, but I want to give you a minute or two to talk about your work in the open source community. I think it's really important to highlight that, since this is all open source work that you're showcasing here.
Yep. So AWS Libcrypto is on GitHub under the AWS organization, as is AWS Libcrypto for Rust, which is our Rust bindings that are built on top of AWS Libcrypto. So the AWS Libcrypto is a C library, C++ library. It's open source. We take contributions, and same with AWS Libcrypto for Rust. If there's some cryptographic feature that's not exposed there, we are open to pull requests or working with people who, even if you're a first-time contributor, there is no limit. Cut us an issue, tell us what you're interested in seeing, and we can try to work with you to figure out if that's the right thing and help you come up with an API that we think would work for Rust users. So,
Sean, we could talk all day. I think you mentioned SIG-v4 in there. We could have gone into that. S2N we could have talked about. There's so many cool
future topics, right?
Yeah, there's some really cool security protocols that happen around here. Signing, methodologies, things like that are really, really interesting, I think, to every security practitioner. So hopefully you'll come back.
Yeah, no, I'd love to come back.
Awesome. Well, thanks for chatting with us today about all the things going on in Libcrypto, and we hope to see you again soon.
Yeah, take care. Thank you,
Sean.